This is Theorem 12. Um, Now, one thing I have to say beforehand is that you can actually quote Theorem 11 as being true for this one, as well as Theorem 13, which is one that gets a bit more challenging. I feel is probably the most difficult one of the three mandatory theorems. So it says, let ABC be a triangle. Prove that if L parallel to BC cuts AB in the ratio S to T, where S and T are natural, it also cuts AC in the same ratio. So we'll start off with our diagram. So we want ABC to be a triangle. Now we want L parallel to BC, so we'll make the base BC, which means this vertex here is A. So we'll have this line going through, and we'll mark that these are parallel. This line L. So after the diagram, we state our given. So what are we given? Well, we're given a triangle ABC where a line L is parallel to the line segment BC. We also know that it will cut at two different points. I'll call it X and Y. I don't know because I'll use them later. So I'll call them D and E. So they cut at D and E. Cut at D and E, where BD to AD is S to T. And what we want to prove is that CE to AE is S to T. Okay? So now we're going to get onto the construction, and this is where like the little trick comes in, because you can employ Theorem 11 into here as well. What we're going to do is we're going to construct several parallel lines such that there are S lines here and T lines here. So construct S lines parallel to L under D through BD. And then we construct T lines parallel to L through AD. So these are all parallel to L. Yep. So what do we do from here? Well, the proof starts by just defining some values. So we just say let x be the distance between two lines, between two lines, through well, under DE, I guess we'll say. Two lines under the line segment DE. So what I mean by that is that each one of these gaps has a width of x. So for B to D, we'll say equals S amounts of x. No, I did that wrong actually, sorry. Is that we just let x be the distance between two lines along the line segment AB. So along AB. My dog better not bark showing this. Yeah, so each one of these is going to represent the same distance. So that means that B to D is Sx and A to D is Tx. We're on the right track. So B to D is Sx and A to D is Tx. Therefore, we can just say that B to D to A to D is S to T. Well, the X can be factored out really, or cancelled, but we'll just say that. That's already what we were given. Now what we can say is let Y be the distance between two lines along AC. Yeah, that means that this distance here, the distance between the lines, is y. Therefore, we can say CE is SY and AE is TY. And all you have to do is quote Theorem 11. Therefore, if we simplify, we'll get that CE to AE is S to T. Now you could go and try reproving Theorem 11 for this, but all you have to do is just say that this is true because of Theorem 11. So we get the results as expected, and that's Theorem 12.